Swayam Prabha. Digital India. Educated India.
Okay, so good afternoon. Nice to see you again. Yesterday we have an introduction about the coastal engineering and also the linear wave theory. And today we are going to talk about natural wind waves. So that's the first part. So after we have learned this one, you will have a good understanding about the generation of the waves and also some analysis of the wind waves. So we will include the process, that's the wave generation, and also we will have a long and a short-term wave analysis techniques. So we will introduce that. And at the same time, we will introduce a simple techniques to estimate the wave parameters. So for example, under certain wind speed, and in a certain water depth, and for a certain range of the water, what wave height will be, and what the peak wave period will be. So that's what we are going to teach, or we are going to learn during this module. So that will be the content covered. That will be the reading. I mentioned like yesterday, what books you are able to read. So now we will see the wave generation by wind. So what factors which will control the generation and the growth of the wind waves? So that's the question we are listed here. So of course, you know wind speed. Stronger wind, large wind speed, more energy. The wave height should be larger, right? So that's first one, we know that. That's the energy which is controlled by the wind speed. And the second one is the fetch. What is a fetch? Fetch is a straight line distance, but which is over the wind blows. So if you have, for example, a small pond or a small swimming pool, even you have the wind blowing on it, you won't get a big wave, right? Because the fetch over there is very small, very small. So that's a fetch, also important. And then we will have another thing is the duration of the wind. So if we have a very strong wind, but this wind just lasts 5 seconds, 10 seconds, then the energy accumulated still small. You also will not get a big wave. So you are able to see those are the key parameters which control the generation and the growth of the waves. Speed, fetch, duration. So they are direct parameters, but also there is a secondary factor, which is water depth. So the water depth over here, which will have the impact on the energy loss. So due to the friction or due to the braking, that will also affect. So that's the things, the key things we are pay attention to. But of course, there are other factors, but that not as direct as the factors listed here. So now we are looking at those factors on the screen. Now we will look at, okay, we know the wind will be, the energy from the wind will be transferred to the water. And initially, when this wind, actually that's the air, movement of the air, which have interaction with the water, and that small turbulence, which has a high frequency, very quick turbulence, transfer the energy from the air to the water. So that's initially. But then because the particle velocity, which is, the frequency is much lower than that turbulence. So those energy will be converted to a little bit lower frequency. That's initially the wave will be built up. And then once the waves propagated further away from where the wind has been generated, then those frequencies will be lower again. If you remember that, we haven't introduced. Later we will see the group velocity transfer those energy away. But these are how the frequency changed during the wind wave built up. So quicker, and then build a little bit longer waves, and then even longer. So that will be if we were looking at this one. So if you look at this, the wind direction, the first one, that's due to the turbulence, you generate the first initial, like a wind, the waves. And then you have the green part. That's because of when it's like a growth. When it's a growth, then it will be affected by the particle velocity, generate the green one. So that will be the green part over here. And then later, when that's propagated further away, and then that will be this one. So the frequency will be smaller, but the period will be longer. So this will be the energy transferred. That also with the time you are looking into. And also you are also can able to look at that with distance away as well. Both the time and the distance. So that will be the energy transfer in relation to the frequency as well. So that's we talked about first thing, which is with the distance. So we mentioned about one. Then here we first look at the distance away from the original, the wind location. And then at the same time, we can also even look at the same location, but with a time change as well. But at the same time, you can also look at both temporal and spatial distribution of the wave energy. Now we come to the classification of the wave. So first, we introduce the first one is a Fetch-limited wave generation. So when we are talking about a Fetch-limited wave generation, which occurs when the times taken for the wave energy to travel the length of the fetch. So of course, this will be the fetch, and this will be the energy traveled. So the group velocity, that's how quick the energy will be transferred. Then the time used for that will be the F, the fetch, divided by CG. That will be the time. If that time is less than the duration, TD is a wind duration, then this is a Fetch limited. Because you don't need such a long time. You just, the wind if blowing to this traveling time, then that will be already the same. So over here, actually, it's not duration limited, it's a Fetch limited. Yeah. So that's the wave growth is limited by the Fetch length. Then we have a second type. That will be the duration limited wave generation. Of course, this is when this traveling time or by the fetch of this group velocity is greater than the duration. Then this will be the duration limited. So with this one, that will be the two conditions. One is F over CG less than TD, duration of the wind. The other one is greater than this. Then that will be the growth of this is limited by the wind duration. So that's the two typical one we are over. Another one we will say is a fully developed C. So that occurs when both the fetch length and the wind duration are not limiting the wave growth. Generally restricted to wave generation in a large ocean basin. So you have a very large fetch. At the same time, this wind will be able to blow for a long time. Then this sea will be fully developed. So that will be the three typical wind wave classifications we are having. So that's a wave. We have all those definitions. Now we will see how are we going to analyze those short-term wave records. So in this diagram, this is a typical measurement. So this is for about 280 seconds measurement of the waves. So you are able to see this is irregular. Yesterday we introduced regular wave, which has only single period, right? But for the irregular wave, there is a distribution of the wave period. So that's like here. So you are able to see each have a very a period, and also the wavelength is different. So it will have a certain distribution of the length and the height. So that will be the first one. So how can we analyze those short-term record? So this is a short-term record. So we are able to analyze wave by wave. That's in time domain. Or we are also able to analyze that in the spectral analysis. So these two typical techniques. So now we look at time domain. So we are doing that wave by wave. So for a raw wave data, so we are able to break that. For example, about 30 minutes waves. So that's typical short-term record. Then when we are doing that, the individual waves we are able to identify by using a zero crossing analysis. So sometimes we say, okay, how many waves in that, for example, in this one record? How can we count how many waves? So this is a wave by wave. Then we will using all those, the crossing point, right? So all those points for us, because that's easy to identify and recognize for those recording, sorry, for those like crossing point. So when we are having that, we use a zero. And some of you maybe say, oh, I can try to identify the maximum, the trough or the crest. But what's the limitation of that? So when those regular waves, you are not that easy to identify when is the maximum, right? Because the maximum magnitude is keep changing. But the zero crossing point is always there. It's always there. So we are using that. But you are able to see even for, I can use this diagram. We have a crossing point. We have a crossing point. We have a crossing point. But for this point over here, we are using is like a crossing up. So we're using that is a crossing up. That's from negative to the positive, is increasing. And of course, then for the next one we identify, we still try to get the other one is also from negative to the positive. So it's up crossing. And for this point, of course, it's not the up crossing. So we are not using that one. So between the next to each other for these 2 points, that will be one wave we identify. So this will be the techniques normally we use to analyze those wave by wave recording. Of course, you are also able to use down crossing. You just keep using down crossing. That's also okay. Yeah. And then, of course, the height and the period for each of the wave will be extracted. Then if you want to say for this chunk or record of the data set, you can get the average wave period, or you are also able to get the average wave height. So for that range. But also you are able to do a certain analysis. So like we are saying the significant wave height, or mean wave height, or root mean square wave height. So all the different statistic analysis can also be done as well. But first you need to recognize that. So like we mentioned this one, so what are the wave and statistic we are using? Maximum wave height. So for those records, you are able to recognize what is the highest one. And also you are able to do the root mean square wave height. So you square the wave height and get the mean, the average, and then get the root, square root. Then that will be the root mean square. Also, you are able to get the average zero crossing period. So that will be the length of the record. If you have 10 waves, and also you know what's the total length of that. If it's, for example, is 200 seconds, you have 10 waves, then your average period will be 20 seconds, right? So that's another parameter you are able to get. And the significant wave height, that's the average of the highest, 1/3. So that's the highest 1/3 of the waves. So a lot of time we are using that as one of the design conditions. So we use quite a lot. So if you are very experienced, for those people, they are able to observe what's the wave height by using the significant wave height. And just now, that's typical parameters or statistic parameters. But also here, we also have a distribution. It's a statistical distribution we are using. And for that, we will use that for our design, very important. Because we are not able just to use one single wave as our design. We have to observe a certain long period. Then we will use that statistical distribution to get our design conditions. And sometimes if you don't have, then we are also using numerical model to estimate the condition. And also, usually we are using is a significant wave height because we are able to convert that, later you will see, to the maximum wave height, or is a 1%, top 1% or top 10%, depends on the design criteria of your project. And so that's the definition we are using. One is we use existence percentage. So if we are using, for example, the average height of the highest 10%, we use H10. And if we use the existence percentage, that will be H10%. Oops. That will be H10%. So they are different. Okay. So one is the average height of the top 10%. It's an average. Another one is H10% specific existence percentile. That's a wave height. So they are a little bit different. So you will see from the next chart. So which one is higher? H10% or H10? H10. H10 because that's all those above those top 10%, they get averaged. And H10% over there, that's just like the boundary. So that's, if we draw on the board, if we rank all of that, so if you have all those data together, you rank that. So this is 10%. So this part, those points are the top 10%, right? And H10 over here, that's average of this data set. Correct? So of course, H10 will be greater than H10%. So that's just a definition. We use a symbol to represent that.
10% is the probability.
Is a probability is a specific exceedance percentile for this 10%. Yeah. So for example, if we know the so this is, for example, is a 3.2 meters over here, is our H10, right? But we have other data set which have 5 meter, 4 meter, 4.5 meters. Then H10 will be the average of those. Yeah. And also we know for the short-term wave record, so this distribution, Rayleigh distribution, which applies to a short-term wave records. So we are able to represent the probability of the wave height exceeding the threshold of x, which is able to use exponential functions to describe it. So that's a typical Rayleigh distribution for a short-term wave record. So that's a probability. And we have all the variables has been defined over here. X, just the ending threshold value, and HRMS, that's root mean square wave height for the total data set you have. And how are we going to use this Rayleigh distribution to estimate wave height existence? So that's the steps. So if you are engineer, you get the record of those data set. You use zero crossing techniques. You are able to recognize how many waves you have. And you know for each wave, what's the period, what's the wave height. So if you're looking at the distribution of the wave height, then you will rank all of that. Okay? So you rank all those wave height, you collect it. So for example, you put the H1, that's the largest. If it is 8.2 meters. And then you have the next one is a 7 meter or 6 meter, and so on. You rank everything. Okay? Then you are going to do the next step. Then you will see the probability of an individual wave height being greater than some height. So that's what we are doing over here. So if the number 1, if it's the number 1, then of course the largest one, that will, if you have a total, for example, you have 100 waves, and the number 1, that probability will be 1 over 100, right? For those wave height greater than the given one, that will be only 1. So 1%. So that's what you are able to define. And then you have the number 2, then you can also define that. So you will get all those probability for each of those waves. So that's the probabilities by using this one. And then you will be able to see for any those ranked wave, H1, H2, so that's a HN, right? So here, this H1, 2, 3, 4, that's different from what we are referring in the last slide, that H10. Here is just a ranking of these waves. Okay, so that's different from the other slides. So this is just a ranking of the waves. Then you are able to see if we rearrange this one for each wave height. If you want to see each of that, you are able to use this one to get the estimation of this. So that's purely based on the distribution. You are able to have this. Then in the application, we just draw the diagram over here. So the line, that's from distribution function. And the dots, that's your wave record. So if all those dot points fit very well with that distribution, that's from this last slide. This is from the modeling, from the fitting, right? So this will be from the distribution model. So if they all fall on the same line, which means they agree to each other very well. So that's what we are using this diagram to show it. And then we are looking at this one. So when we are looking at the Hmax, the maximum wave height, so we are able to have this relationship. So that's the maximum. And at the same time, if we are using H significant height, then approximation will be square root of 2 of the HRMS. And the same thing, you have the average or mean of that is a 0.886 root mean square. And then for any the percentile you want to get, that will be this one. So that's a relationship we are able to use. But then again, we are able to use this diagram. So one is A, one is a B. So A is what we are talking about. That's H X%. And the B will be the HX. So that will be the two lines we are able to use for the design. So a lot of time we use this figure to help us to identify or to calculate the wave height of your design condition. So now I'm going to use an example to look at how are we going to use this relay distribution to calculate. So a wave record is analyzed using zero up crossing method and contains 205 waves. So we're using the techniques, and that's the techniques we used. The average wave height is 1.72 meters. That's a given condition. We're assuming a relay distribution of wave height. Now, we ask you to estimate the significant wave height. The wave height existed by 5%, and the average height of the highest 5%. So that's H5% and H5. And the number of waves in the record that would exist a height of 2.5 meters. How many waves which have a record greater than 2.5 meters? So how am I going to do that? So we will work together on this example. So first we will look at what are the given conditions we are having. So given conditions we are having, okay. First one is a number of waves. So which is n equals 205. And then we have average wave height. So which is 1.72 meters. So that's a given condition. Now, first thing, I will estimate significant wave height. which is HS. And also here, the HS we defined is average is the average height of the one-third of waves. Okay, so that's the first condition. Is that too small? It's okay? Okay, yeah. And then we enter the charge. So then I'm going to use the charge. So the chart we are having from the vertical axis so where n equals 1/3. And then next go across horizontally to line B. And read off so if I going up, I will see. So we are using this one, right? So we are using this line. So we find out 1/3. Roughly, this is a 0.5, 0.3, 0.1, 2, 3 is roughly here. So then we got cross here, right? Then if you're going down, yeah. So this is a 1/3, 0.33, right? Yeah, and then we will cross this to the B line over here. Then we will reading, that's what we are having. So we will have this one, H over HRMS over here for significant wave height. That will be what we are having. Okay, so I go back to the lines over here. Then we will have, so over here we will have here for n equal 1/3. So that's a significant wave height. We use the B line, which means that's for the average top 1/3. Okay. So HRMS equals 1.42. So therefore, we will have H significant 5. So now we have this relationship. But now we want to know what is HRMS. So now we need to find out what's this, right? So next thing we will see, given we have another condition, remember, over here. We have the average wave height, that's 172 meters. That's given condition. And sorry, HRMS equals to,
The square root value of this h bar squared will give you the HRMS value. We have average wave height, h bar is 1.72.
yes,
And if we use the relation what is shown before, like HRMS is equal to square root of h bar squared.
yes, we have that relation as well. Yeah, so we have this. So that's what we are having this, yeah. So we are able to use the equations underneath. We have okay, we have that one, RMS equals to what? Over 0.89, which will be 1.72 over 0.89, which is 1.93 meters. Now we have this root mean square wave height. So based on these two, we are able to get significant wave height will be 1.42 times 1.93, which is 2.74 meters. So that's, we just based on all those given conditions, we are able to get the estimation of the significant wave height we are having. That's a first part we have. Now the second part, what we are going to do is estimate H5%. So that's a height. That's a height exceeded by 5% of waves. So the top 5% of the waves. And again, by using the Rayleigh distribution, so we will have so what's the n over n over here? We have that is 5%. And also by using this, we are able to have so 1.93 meter, and then that is a minus log 0.05, which equals to 3.34 meters. So that's a 5%. Now we will look at next part. So this is 3.34 meters. Then if we look at the next part, which is estimate the, so I go to the number 3, we estimate H5, which is the average height of the highest. 5% of waves. So that's a difference. So again, this time we will know n equals 5%, which is 0.05. And then we will using the intersect. So 9b, we will see that, okay? What is the 9b? 0.05. I go up to this line again. So for this line, what we are having over here, 0.05. 0.05, that's over here. Correct? That's roughly 1.9 something, because the scale here is too rough. So we need to have like a finer the tick resolution to get more accurate. So over here, that's the way we are using this one, 0.05, to find the line B. So the before, this is a, and here is a 5, okay? So we will be able to see, okay. By using this, we are having and I go back to here. So we think the intersect with this line, we will be able to have H5 over HRMS, which roughly is 1.97. Therefore, we will have H5 will be equals to 1.97 times 1.93, which is 3.8 meters, 3.81. Correct? So, and also you are able to see, of course, H5, which is greater than H5%. That's as what we expected. So next step is to see the number of waves. So number 4 is try to get the number of waves that exceeds a height of 2.5 meters. How many of the waves we are having that? So when we are doing this, we will see, okay, what we need to find out actually will be the number of waves exceeding, which is a total number of waves, so times the probability . So how are we able to do that? So we will write that in a mathematical format. That's number of the waves, which have the wave height greater than 2.5 meters, which is number of the waves, that's the total number of the waves, times probability. So that will be the h greater than 2.5 meter. So that's what we are looking into. So now the thing is the probability. How we calculate the probability? So where the probability of this for h greater than 2.5 which will be equals to, that will be the exponential function, that's a relative distribution. We will have this one. And also this is a given 2.5, and this is HRMS. So this is just a purely use a Rayleigh distribution, okay? So of course, once we know this, that's easy for the calculation. This will be exponential, this will be minus, oh, I forgot a square over here. And then this will be 2.5 and RMS and square. This will be equal to 0.1876. So this is a probability. There's no unit, okay? Just you have about nearly 19% chance to have the waves greater than 2.5 meters. The next step, that's easy. So you are able to get the number of the waves greater than 2.5 meter, which will be equal to 205 times 0.1876, which is 38.45. Then, of course, it will be round off to 38 waves. So that will be the final answer. So we will roughly get 38 waves, which is a wave height greater than 2.5 meters. So that's another way for us to use a short-term wave analysis to analyze some waves. So that's one way we are using. Any question? For the last part? No, because this one you already know, like you know the given wave height. You want to count how many waves above that. So for that green wave, that's normally for you to find out the ratio between these. Yeah. So then you are able to using this ratio to calculate those existence average percent, the wave height. So we can use either A or B lines. Okay, so if no question, then we have 10 minutes break. Then we will come back. Thank you.